In this video, I want to talk about cost functions. And to start, I want to show you the difference between what we did in consumer theory here versus what we're doing with producer theory. So if you remember, or you should remember, consumer theory had us answering a problem that dealt with maximizing utility, which is some function. I gave it a Cobb-Douglas utility function here. But that was subject to, this ST, subject to our spending had to be equal to our budget, how much we were willing to spend. So we were constrained by this. Now in producer theory, though, we're minimizing our costs, how much we're spending, or how much the company's spending on our two inputs, typically labor and capital. So cost is W1X1 plus W2X2, almost like the budget. But now this is subject to Q equals and then some function. Again, I put a Cobb-Douglas, but it can be any function. So this is the constraint now. Now, if we were to write the Lagrangian, it would just look like something like this. Big L equals W1X1 plus W2X2, and then plus our delta or Lagrange multiplier. And remember, we wanted the constraint to be equal to 0. So I'm just going to subtract the technology that we have here, AX1 to the alpha, it should be just X2, sorry, to the beta. So this is how our new Lagrangian would look like. And this can be a little complicated, mainly because of our constraint. We'd have to be solving, doing a lot of math, really. Your book has an example, and it's not too bad, but when you start putting, different exponents for A and B up here, like 0.2 and 0.3, you're now taking the 0.2 root of an equation, and that's not something we typically deal with. So to make it easier, what you really need to know is how to solve this Cobb-Douglas equation really with just the short run. For the other technologies like linear and perfect substitutes or perfect complements as well, we have equations, and you'll use them from the slides. All right, so I'm going to start with the example, but I'm going to do it easier. So this is an example, not with Cobb-Douglas, but with our a linear perfect substitutes technology. So Q equals 5x1 plus 2x2. And you might be given something that says x2 bar is fixed at a certain number, here 6. What that means is this input, maybe our capital, is fixed at a certain level. Maybe we have 6 machines to create our output. And labor, maybe X1, can vary. So we can have 2 people today, 5 people tomorrow, 0 people the next day, and so forth. That can vary. Now to solve this, we want to take what we know about X2 and plug it right into the production function. So then we'd have Q equals 5x1 plus 12, right? Then we just want to solve for x1. We want to get this by itself. So 5x1 equals Q minus 12. And then we want to divide out 5 on both sides. So we have Q minus 12 over 5. This is our conditional demand for x1. Given how much we want to produce, this is the function that tells us how much we're going to use of x1. Now the cost function, we want to put that all together. So cost is a function of both wages and our output, how much we want to produce. And that equals, we take now what we have for x1. We know what we spend is going to be W1 times X1, but now we just want to put our Q minus 12 over 5 in here. That doesn't look like 5, does it? And then since we're going to add how much we're spending for X2, that's W2 just times 6, since that's fixed. And this would be the final cost function. Now, what does it mean if we have X2 fixed at a certain level? As we said, it was fixed. That also means that we're going to have a fixed cost, right? So this is going to be a constant number if we knew W2, at least for a time, right? That means altogether we have a fixed cost and we're also in the short run. So you want to remember that as well. Now I'm going to get a new page. And then let's do one that's Cobb-Douglas. So we have maybe Q equals square root of x1 times x2. And I want to rewrite this. This is also just equal to x1 to the 0.5 power, x2 to the 0.5 or 1/2 power. And then we have x2 fixed at 4 units. Again, we want to find the cost function. So I've been using x2 as being fixed, doesn't matter, right? And just one of these is fixed for the problem. Now let's plug in our 4 in for x2. So we have Q equals x1 to the 0.5 or 1/2 power, and then 4 to the 0.5. Now, as we said over here, the 0.5 power is just the square root, and we know what the square root of 4 is, and that's easy. So this is just x1 to the 0.5 times 2. Not bad. And just like we had before, we want to solve for x1. So we want to take our 2, divide it out. I'm going to switch this over, x1 to the 0.5 equals Q divided by 2. And then how do we get this 0.5 exponent out? Well, we want to square each side. That would leave us with just x1 on the left. And then we can just write Q over 2 squared, or you can put the square in here. It'd be Q squared over 4. Either way is fine. And lastly, we just have to find the cost function for this. So again, W1 times what we just found for x1 plus, and then we're using 4 for x2, and we want to multiply it by W2. This would be our cost. And the cost function should only have W's and Q's in it. We should not have any X's, whether we're in the short run or the long run. All right, hope this helps.